Hello, side camera. My name is Ben, and this is my homework 4. Let's go ahead and get going on part 2. So I am going to implement functions for calculating dew and bubble temperature using the NRTL activity coefficient model. So that's what I just did up in part 1 in the last video. And so I'm going to then apply these to calculate the dew and bubble temperature of an equimolar mix of methanol, ethanol, and water at that many pascals, which I believe is atmospheric pressure. What are the corresponding compositions of the first liquid drop and the first vapor bubble drop in that form? So, awesome. There's really going to be 3 parts, not 3 parts, but there's going to be sort of 3 subparts to this part 2. The first part, I'm going to calculate the bubble temperature using NRTL. The second part, I'm going to calculate the dew temperature using an ideal model because the dew temperature is kind of hard. And then I will use that to make some guesses so I can solve the dew temperature in an activity coefficient model. And all along the way, I will calculate the compositions, the corresponding compositions of the liquid and vapor bubble drop. So first off, real quick, what are dew and bubble temperature? Well, I think this is actually a great graph to kind of show it. You see that if you have maybe a multi-component system, in this case, let's just say it's 2 components, you can say that, okay, when your mole fraction in component 1 is 0, so you're all component 2, then your boiling point of a system is going to be the boiling point of component 2, and then vice versa at component 1. And so this curve kind of shows how you have a gradual increase at which, as you sort of elevate the temperature, which is on the y-axis here, you will see that the dew point will increase. Well, that's not. Yeah, so the dew point will increase, and then the bubble point will increase, and in this middle you have like a zone in which it's boiling, in which some of the component is going to boil, and some of the other component isn't going to boil. Or some, like component 2 is going to boil, component 1 won't boil. So we want to look at this for a 3-component system, and there actually is an azeotrope in this system, which is where these dew point and bubble point lines would intersect. Well, actually I don't think they would intersect, but I'll explain an azeotrope in more detail later. An important thing to keep in mind for what I talk about as I go through this problem is that for a single component, the bubble and dew points are the same and are referred to as the boiling point. So you can use boiling points to get an approximate idea of where the dew and bubble points are going to be, right? You know that the dew and bubble points are always going to fall in between the boiling points of the lowest boiling component and the highest boiling component. That just makes logical sense. And so, with that in mind, let's go ahead and let's go back to homework 4. So I made a little chapter for everything I did in part 1, and I still have this imports and installs, and I cleared my run and reran everything. And so I just have a few things just to begin with, so I'm not having to type this all out. I'm going to say that similarly to before, P is just these properties. Z, which is my feed condition, so it could be liquid, it could be gas. I'm going to use Z for both X or Y, depending on whether I'm solving for a gas system's dew point or a liquid system's bubble point. And then we have a temperature, which is just something that tells us, the pressure, which is something it tells us to use in the problem. And then gamma, which is the activity coefficient. I'm going to use the Einsum activity coefficient. And then for vapor pressure, I'm going to use this PVAP, which is actually built in to the CHE4 library I imported earlier. So with all that in mind, let's go ahead and maybe get started on the bubble temperature, or the bubble pressure and temperature using the NRTL activity coefficient model. So if I go in here to some of my notes, I just made a few quick notes that I sort of copied over from Wikipedia. We know that Raoult's law, when you remove the term about fugacity, because we're going to disregard that for now. Raoult's law says that the mole fraction of the gas of each of the components in the gas phase times the pressure of the gas phase. So this could also be written as the partial pressure, P sub I, the partial pressure of any component. It's just going to equal the fraction in the liquid phase times the activity coefficient, which we just calculated in the last video, times the vapor pressure, which we already have a built-in calculation for. So if I wanted to maybe use the NRTL activity coefficient, this gamma over here, to solve for the partial pressure, to solve for this yi and p, what I could do is I could say that the partial pressure, so this yi times p, is just going to be equal to that. I know the x, I know the gamma, I know the saturated vapor pressure, and then I can solve this pi into yi just by knowing that the total pressure is equal to the summation of all the partial pressures. So that makes pretty intuitive sense, I think, and that's pretty standard thing to know in chemical engineering. So I'll go ahead and maybe say a define. I will define the function maybe bubble px, so a function that returns to me the bubble pressure and the composition of the liquid phase. Well, actually it should be py, should be the composition of the gas phase. And then I will also maybe make a note that this is being done using the NRTL activity coefficient. And then what do I need to specify? Well, in order to get the pressure, I need to specify a temperature, and then I also need to specify the components fractions. So that would be x and t, right? So then what do I want to return? Well, I want to return a value for the pressure, so the total pressure of the total bubble pressure of the system at that temperature, and then also a function for the not a function. I want to return a value for the composition of the first gas bubble. So with that, let's do what I talked about earlier. I can say that maybe the partial pressure of each of the components is just going to be the mole fraction of the components times this gamma and then pvap, or the vapor pressure. So I'll go ahead and put that in and tab it over, and so I can just copy these variables over, right? And then the vapor pressure, so the activity coefficient times the vapor pressure. Then I can say that the pressure is just going to be, I'll use numpy's sum function of all the partial pressures, and then I'll just say that the gas mole fraction is going to be, and I'll change this to a yi down here, it's just going to be the partial pressure of each component divided by the total pressure of the system, right? So I can go ahead and run that, and then I'll come over here and maybe copy this, copy it, not hit V. Copy that, I'll put in Z for my compositions, since I've already defined it that way. T should already be defined up here. So at 300 degrees Celsius, an equimolar mixture of methanol, ethanol, and water should have a composition. The first bubble should have this composition, and the first bubble should occur at this pressure. Well, that's sweet, but what I want to find is the bubble temperature. So I need to create a similar function to this, but instead of just giving myself a pressure, I need to provide myself a pressure, say atmospheric pressure, which is what this pressure is up here in pascals, and I want to return and I also need to give it a composition of the liquid, and then I want to return a temperature. Well, how could I go about doing this? Going back to my notes, you can see that we can shift the formula around and we'll get the saturation vapor pressure, which is a function of temperature, right? So this is directly related to temperature. It's just going to be equal to the pressure, the partial pressure of each component over like this gamma and the x. So what I need to do is I need to use a solver to find temperature, knowing this function over here, this bubble pressure function. So I guess maybe let's go within this function I've already defined. Let me define a new function, and this is just for solving purposes. And this function will take in a value of t, which is what we're trying to solve for. And then I will go in and I'll take in a value of t, and then I will evaluate, say, this bubble temperature, or this bubble pressure I've already defined before, and I would just evaluate that at x and whatever value of t is provided, and then I can just return that, right? So I've sort of repurposed this function down here. But what I want to say is I want to use a root solver to find this. So I want to find not just any value of this function, but I want to find the root of this function when it is equal to whatever pressure. So I'm going to subtract off the pressure, which basically will tell me that when this EQ function that I've defined right here is equal to 0, well, that's the point at which the temperature is equal to the bubble temperature for a component or for a system with these components, right? This X components. So with that in mind, I could try to use a typical root solver to solve this out, but I'm going to try using something called BrentQ. And BrentQ is a root solver that takes in, oh, I actually have, yeah, okay, so SciPy optimized BrentQ. I already imported it. It's going to take in a function, and then this A and B value. And this A and B value is an interval that tells you to, over this interval in the independent variable, find the root of the function. So this is going to be pretty helpful here. The problem is, how do I get an interval for the temperature? How do I know like a range at which the bubble temperature has to fall in? Well, this falls into what I talked about earlier with the bubble point, right? The bubble point is always going to be between the boiling point, the lowest and highest boiling point of the components of the system, right? That makes intuitive sense. It has to be that way. So I can come in here and I can maybe say I can go to that function that I can go to the properties of P, and I can look for the TB, which is the temperature of the boiling point at whatever pressure I specified. That's like a known temperature. That's like a known boiling point temperature that my professor is that the library can calculate. So I can say at a given pressure, what's the boiling point of the system, or what's the boiling point of each of the components in here. It's not the boiling point of the system or of the mixture of the three components. It's just the boiling point of each of the three components. And then I can call that maybe P underscore TB. I'll set that equal to that. So now what I can do is I can say that the lower bound, so maybe I'll just say the TB low and then the TB high are just going to be equal to the numpy's minimum of this minimum, or the lowest boiling point of the three components, and then vice versa, or similarly, I shouldn't say vice versa, I feel like I say that a lot, but the maximum of the three boiling points. So now I have these low and high bounds defined, so now I can go in and BrentQ, and I can say that the function is just going to be the EQ as I just defined it, so this equation, and then I am going to give it a low value for A, and then a high value for B, and that's the interval. And so now this BrentQ should return to me like the value of the, it should return to me the temperature, whatever value of T makes this return equals 0 when you're looking at this function. So I can go ahead and maybe run this, and let's see if I go ahead and copy the function name down here, and then I copy a Z. So at the certain value of Z, or at a certain mixture, what happens here? P, it didn't like this a little bit. Okay, it looks like I have, okay, so first off, you have to keep in mind, I'm returning the pressure and the mole fractions of, in this function up here. So instead of just calling this function, I need to call just the first value of that function. So I can go ahead and run that again, and let's see, it should work. Yeah, I get, at a set pressure, well actually, okay, let me copy the pressure from what I calculated here with the Z and the T, and now when I run it, I get 300 degrees for T, which is what I defined up here for T. So this function is working, it is calculating the temperature correctly. Let me go ahead and maybe comment this out. I'll leave it just there, but I'll comment it out. And I'll go ahead and say that the vapor, the bubble temperature is going to be equal to that, if I can find it, right? So that's the bubble temperature. But then in addition to returning the bubble temperature, I also want to return the fraction of the first bubble, right? Well, yeah, I want to return the fraction of the first bubble. And so how can I go about doing this, right? Well, since I already know the initial concentration and the temperature, I can just go up here to the function. I can call the bubble pressure function again, and I can just say that yi is going to equal the bubble pressure evaluated at that temperature, evaluated at the initial conditions, this x, and yi is just going to be the second value that returns, because yi is the second thing down here. So if I go ahead and run this again, redefine the function, now if I run it at that pressure, I should get, oh yeah, look at that, the compositions of methanol, ethanol, and water are the same, whether I'm running it between the two conditions, because they're like equivalent bubble points. So sweet. That is the first thing I wanted to do, which is calculating the dew or just the bubble temperature using the NRTL activity coefficient model. Moving on, let me take a look at the ideal dew point. So instead of using the NRTL activity coefficient model, I'm just going to ignore the activity coefficient and assume it's an ideal mixture. Why am I doing this? Because to actually calculate the dew temperature using the activity coefficient model is a little bit more complicated, and I need to use the ideal ones as a guess. So let me maybe delete this and this down here, and I'll come up here and I will say that, I'll say that I want to define a function that returns the dew, let's start out with dew pressure. I think that would be best. So I'll start out with the dew pressure. And then I also want to return the composition of the first drop of dew. But instead of using the NRTL, I will just use the ideal model, right? So I will need to give this dew pressure. I will need to give this the composition of the vapor phase, and then I will also need to give it the temperature, or wherever it is, right, to calculate the pressure. So then how can I go about doing this? Well, I did some math over here, right? I'm going to say that the fraction of component I times the, or the partial pressure of component I, or the vapor fraction of component I times the total pressure is just equal to the, at the dew point, is going to be equal to the gas, or the liquid composition, the liquid mole fraction times the saturation vapor pressure. So of course I can just rearrange it to get this, and this will let me calculate the saturation of the liquid composition of a dew point, or of the dew point, or of the dew point pressure. And then I just know that the summation of all the x's is going to equal 1. So then I can just take the summation of this term over here, and I can say that the total pressure, which won't change throughout the summation, is just equal to all these things. And then rearranging it, I can find that the total pressure is just the summation of, it's the summation of this. So the saturation vapor pressure of each component divided by the gas phase composition of each component, or 1 over what I have right here. So let's go ahead and maybe punch that into the system. I can say that the pressure is going to equal the sum of, let me go ahead and maybe say 1 over the sum of, 1 over the sum of the gas phase composition of each component, or the gas composition for each component, and the saturation pressure for each component at a certain temperature. So I will just say y divided by pvap. But actually, this pvap is something that I've already defined up here. Let me come up here, and just to sort of keep my math consistent, I'll use the same notation. So then that's the pressure of the ideal system at a certain component x, or no, at a certain composition y and a certain temperature. That's the pressure. How do I get the partial pressure? Well, the partial pressure which I'll maybe call pi. You know what? I called it lowercase pi over there. Fair enough. Well, that's just going to be the fraction, or the gas phase composite. I am just screwing up all my words today. Anyway, I don't even really need to calculate the partial pressure, I don't think, right? Because the other thing I want to return is the value of each component, right? So I will just say that x is going to be equal to, let's go back over here and look at the math. That would just be the fraction of component I divided by the saturation pressure, or it's basically the partial pressure times divided by the saturation pressure would be the liquid fraction. So that would just be the pressure times y, and then I think I need to put that in parentheses just to make sure it multiplies through correctly. So once again, this pressure is a scalar, it's just a single value, but this y is an array. It has 3 components in it. It has 1/3, 1/3, 1/3. That's what y would be for the system we're looking at here. And then I'm going to divide that by the saturation vapor pressure. So now that's P, that's X. I can go ahead and return P and X, right? So go ahead and return that. Let's test this out, see what happens. Create a new thing down here, a new cell, and run this with Z. So this is going to say that when you have an equimolar mixture that I've described before at a temperature of 300 degrees Kelvin, that the dew pressure is going to be, so the pressure you would have to lower it to in order, or the pressure you'd have to raise it to in order to get some of the mixture to begin to liquefy. To get the first drops of dew is going to be this pressure in pascals right here, which is pretty darn low pressure, right? And then the components are just going to be these 3 things right here. So now I can do something very similar to what I just did before to get the bubble temperature, to get the dew temperature. I can go ahead and maybe define a new dew temperature with ideal, so ignoring the activity coefficient. I need to give it a value of y and then a value for the pressure, right? So I can't just go calculating the vapor pressure right off the bat. I need to do something similar to what I did before and use a solver to back calculate T, right? So let me come in here and I will say that, I will start off by maybe defining a new equation. So I'll just define a temporary solver equation. That solver equation will take in a value of temperature, and it will return the dew point, the dew pressure of that ideal temperature. So that would just be with a 0 because we just want the pressure. We don't want the mole fractions for this part. And then of course I would just subtract whatever pressure I'm trying to solve for, and then the 0 whenever this equation returns a 0, well, that's just the dew temperature, right? Or according to an ideal model, which isn't really correct, but whatever. So I can go through here and I can do something similar to what I did before. I can calculate the boiling points of each one to get a bounds for what the temperature should be. Then I will come down here and I will say that Brent Q of the equation bounded by the I shouldn't have said the, I was about to copy paste the wrong thing, but bounded by the lower and the higher boiling point temperatures will always give you the will return to me the actual value of the temperature. So I can maybe come in here and just print this for now, and let's see what happens when I just print it. Go ahead and run that. I will take the dew temperature and fraction, and let's see what it returns to me. Oh, y is not defined. Okay, yeah, it should be a z in there. What happens then Okay, so now I get a temperature, and that temperature is not the one that I initially passed into the function. So something is being done incorrectly here. Boo-hoo. That's tough. Tough scene. So I think I actually messed something up in here. So I said that the pressure should be equal to 1 over the sum of yi divided by the saturation pressure. Did I do that correctly? Yeah, I believe I did. And then I said that x, well, x doesn't matter. I haven't even, I mean, the x's all add up to be 1 when I did it down here, so it can't be, at least I didn't mess that part up. But, at least they look like they add up to 1. I haven't done the math, but, well, you got like, I think those add up to 1. You've got these add up to about 0.4. This is about 0.6. It looks about right. So the pressure is going to be 1 over that. Yeah, so I checked it on this and actually didn't do anything incorrectly. I was just putting in the wrong temperature and pressure back in to the system to find that these two are sort of inverses of each other. Anyway, let's go ahead and move on to the last part of this section where I'm going to finally figure out the do NRTL activity coefficient. I just added in a little title there. I can go ahead and maybe restart the runtime and run all real quick because I was messing around with this for a few minutes and I just want to make sure the runtime is straight again. Should probably take a second to run everything because a lot of those cells require importing some stuff, and we're good now. So as you can see, the dew pressure at the ideal dew pressure at 300 degrees Kelvin will return this pressure, and so then the dew temperature returns something likewise. So before I move on, let me go ahead and I will maybe say that this right here returns to me, this Brent Q method returns to me the temperature, and then I can go ahead and evaluate this temperature at certain values, or I can go ahead and say that I want to take the, I want to get the xi, so I'll say I want the second value from there and set that equal to xi, and then I will go ahead and return t and xi, except t needs to be capitalized. Sweet, so now when I run this, I should get 2 arrays showing, yep, the same compositions at both forms. So that's great. Let me go ahead and move on to this NRTL section now. So I want to define a function that will take the dew point. Nope, that's not it. There it is. I will take the dew, it'll get the dew pressure and the composition of the first bubble, but this time I want it to be using the NRTL activity coefficients. So let's go take a look in Paint real quick. So this is what Rouseall looks like with the activity coefficients, right? We've got, we've got all these variables. I've talked about them before. But the problem is that this gamma, right, the activity coefficient is dependent on the mole fraction of each one, right? Gamma is going to change at different mole fractions. So we have to create some sort of solver to actually determine what, say, the partial pressure would be, and then we can use that, we can sort of do that in reverse to solve for the temperature, for the ideal dew temperature. But anyway, that's all fine and good, but let's go ahead and start coding this out, right? So let me create a second just solver function, and I'll just call the equation, and I will give it a temperature in this case, and I want to return some condition at which, let's say that the partial pressure of each component minus y times the total pressure. I want to return that so that I can set this equal to 0. So with that in mind, how do we calculate the partial pressure? Well, I can just say that the partial pressure is going to equal, and I will reuse some stuff that I already said before, right? I'll maybe come back up here and I'll say that partial pressure is just going to be all this stuff right here. So let me copy that and then go ahead and paste it down here. So I can say that, yeah, the gamma, the vapor pressure are defined as such. Do I know X right now? No, I do not. And that is sort of the issue with trying to solve this out, right? Because I need to, first off, I need to pass in values of the composition and values of the temperature into this function. But then I only can pass in one variable. Well, the best way for me to do that is instead of just passing in the temperature directly, let me pass in a vector, v, or actually, let me call this q, actually. And then I will use something my professor built in to the library called, it's up here somewhere, q to x and x to q. So this is just doing what I did in homework 3 before, right? Where if I have 3 compositions, right? I've got an x1, x2, and x3, then I can represent that as q1 and q2, and then q3 is just what I did before. But go check out my video, go check out my homework 3, and it'll sort of explain what I'm going to do here a little bit more. So I'm going to say that x is just going to be q to x of q, but then it's not going to be all of q, it's going to be all the values of q except for the last one, because this last value of q I am going to use for the temperature, right? To pass the temperature into the function. So that is the due pressure. Let's see, is that what I'm trying to... Yeah, okay, that's what I need to start out with, is the due pressure. Yeah, I'm doing that correctly. So now I can calculate gamma, I can calculate the vapor pressure, I can calculate the partial pressure from that, and now I can find when all the partial pressures are 0. So now I can go ahead and maybe get a root solver, and I can say that my function for the root solver is going to be the equation, and what should my initial guess be? Well, that's where this ideal due temperature comes in a lot of handy, right? I can say that my ideal, well, I shouldn't say, I'll say that maybe the P ideal and the fractions of x ideal are going to be equal to the results of the ideal, this function I derived up here, yeah, P and xi. So those are the ideal ones, and then I can use those as a guess for this function root. But what do I need to pass into equation as my initial guess? What form should it take? Well, it's going to look something like this. It's going to be all of these ideal x values converted to q values. So I can maybe say that x to q of x ideal. And then on top of that, I need to actually append in the underscore, or I need to append in this ideal pressure that I've derived, right? So I'll go ahead and maybe use np.append, and so I set an array right here. This is an array of 2 values, a 2-value array right here, and then I add on a 3rd value into that. And so now I have a guess, so I'll just maybe call this guess. And then I will go ahead and bring guess down here into the root. And let me maybe go ahead and print this root, and let's see what I get. Right, sweet. So I can go ahead and maybe run the function now. I will run it with the feed conditions, and I get a big long chain of values, but it returns to me, well, let's see. It returns to me 3 things, right? The first one, and this is Q1, this is Q2, and then this is the pressure, right? So maybe let me go ahead and take just X here. And then on top of taking just X, let me maybe take this root, right? And I will copy this out of here. And I will say that the Q's are just going to be that root. And then I will say that I'll say maybe Qi, even just to differentiate a little bit more. Xi is just going to be Q to X of Qi, right? So I'm transforming this Q variable back into an X. And then I have, yeah, let me try to print off maybe just the X's real quick and see what that does. That should not quite be correct, right? That would, yeah, that obviously is impossible. And that's because, oh, I haven't, yeah, okay, so I haven't set up this Qi correctly either. I need to say that, I shouldn't say that the Qi is all of these root values that it finds. Instead, I should just say it is all the values except for the last one. If I can hit a negative sign. There it is. So it should be all the values but the last one. Let's see what this gives me now. Okay, sweet. So this is also probably not correct, right? This is saying that the first drop is composed entirely of ethanol, I believe, right? So that that just can't be correct. Hey, so I'm back, and I made a few small mistakes. First off, up here I was calling T. I was calling this last thing in here the temperature, when in reality I wanted to call it the pressure, because I'm trying to solve for the pressure in this NRTL dew pressure. Makes pretty intuitive sense, but that was the main mistake. And then I sort of set up the function to actually return pressure and the initial, or not the initial, but the concentrations of each component in the first little drop. And this is the pressure that I ended up getting in pascals. And then this is the composition I ended up getting. So let's move on, and let's do something similar, but for the dew temperature. I can go ahead and just copy this whole thing, right? And I can copy it down here, and then, or paste it down there. I will change it to the dew temperature and composition. I will give it a pressure. Then here now, I will call the last thing in this Q a T, because, yeah, I'm trying to solve for the temperature now. Let's see, I still calculate gamma. I can still calculate the vapor pressure. And then I still calculate the partial pressure and find when the partial pressure is going to be equal to 0. And so now, let's see, where am I at now? I calculate, oh, I think I'm missing something in here. Well, actually, I think I'm good. So now the ideal pressure is going to be the first component of this. Is that correct? Yeah, the ideal pressure, I'm going to make a guess for the ideal pressure. I'm going to append that guess so that it fits into the function the right way. Then I will set the result of the root function to be this translated pressure and concentration variable. Then I'll just parse out the pressure and concentration variables, but I'll need to change this to T and this to T. And with that, I think I should be good, right? Oh, actually I need to change this to the dew temperature and give it a pressure, because I need to find the ideal dew pressure and temperature. But yeah, with all that, I should be good. Go ahead and run that. Let's go up here, maybe take this, but what am I doing? Why am I scrolling all the way up there? I don't know. Go ahead and take this dew temperature NRTL. Let's go ahead and run it with Z and maybe a pressure of this pressure right here. So run it with that pressure, and then the result I get is, yeah, look at that, just around 300 degrees Kelvin. So with that, let's go back and let's look at the actual problem. Apply these to calculate the dew and bubble temperature of equimolar mixtures of those things at 101,325 pascals. So I want to calculate the dew and bubble temperature. The dew temperature is something that I have down here, right? So I will just give it the pressure I specified before. And so the dew pressure, the pressure at which an all-liquid system, as you begin to pressurize it, will form its first drop of vapor, is going to be 351 degrees Kelvin. And then the concentration of the vapor is going to be those when it's methanol, ethanol, and water. So then I need the bubble temperature as well. The bubble temperature, I think, yeah, bubble NRTL is up here. So I'll make another code cell, and I will just take this, the bubble temperature and composition. The pressure should be good, yep, and so I can just go ahead and run this, and yeah, that'll say that the first bubble of an all-liquid mixture, as you are gradually increasing the temperature at a set pressure, the first bubble of liquid will appear at 347 degrees Kelvin, and it will have that composition. So yeah, this mixture of methanol, ethanol, and water will boil between 347 degrees Kelvin and if I can find it, yeah, 351 degrees Kelvin. So yeah, sweet. That is my part 2. I'd like to thank you very much for watching. I hope you learned something, and I will see you again in part 3. Bye-bye.